Hello, welcome back everybody to geometry. Today we will try to conclude as much as possible as to similar triangles and how do they work, how do you prove them, and what can you possibly do with them. So this is going to be, I guess, the second to the last section. So the last section is more of a discovery thing. So we'll try to fill in as much of the void as possible in this case then, okay? All right, so as promised, we're looking at section 5.5 in the Jergensen book, which is the same thing as 12.4 in the Moise book. And the title, as it says right here, is on SAS and SSS similarity. Now, back in the first semester, we learned how to prove two triangles are congruent if they are SAS congruency or SSS congruency. So for similarity, we actually have something on par with that also, similar if you would, I guess, pun intended. So here is an example where two triangles are going to be similar to each other because their sides are all proportional to each other. So notice the triangle on the left, we have a 3, 4, 5 triangle. And then the triangle on the right, we have a 6, 8, 10 triangle. Now, if we overlap them, then we can definitely see that they are actually proportional to each other. So here, let me see if I can kind of show that right here. If I can kind of overlap them, you can see that, the triangles are going to be almost, well, actually, they are going to be similar to each other. So that's what I need to prove. In addition to that, here, because to verify that we actually have an SSS is because we actually have all three sides of each triangle. So you can see how we have three, oops, sorry, wrong one. We can say that side of 3 divided by 6, so 3 divided by 6 is equal to 4 divided by 8, and then that's equal to 5 divided by 10. So you can see now because of that, then that means that the two triangles are similar to each other. So we will talk about the proof of that in just a little bit then, okay? Then we can also consider what happens if the two triangles have something called SAS similarity. So that means that two of the sides are going to be proportional to each other, and the angle in between them, now be careful in this case, the angle in between them is not proportional, but rather congruent, because then that means that we would have a different triangle in that case then, okay? So in this scenario, you can see we have these two triangles to each other. And if I overlap them, then you should be able to kind of see also that they are going to be similar to each other. So that's what we're going to prove. Now, in the given over here, you can see the proportionality according to the sides right here. We have 6 and 12 right here. So 6 divided by 12 is equal to 5 divided by 10. And if the angle in between them are congruent, then that means that we have this SAS similarity. So you can see how it's very similar to SAS congruent triangle then, okay? All right, so before we actually prove them, we need to kind of recap a little bit from the last section, so then that way you can be brought up and see how we can actually prove this stuff using the stuff from the last section. So the last time we talked about something called, well, there's no name for it, but it's called Theorem 12.2. Which says that if you have a triangle and you have a point D on one side and point F on the other side, such that DF is parallel to BC. So you can see on the right, left-hand side that the third side is parallel to that inner segment of DF. So if all those conditions are given, then the conclusion is that AD over AB is equal to AF over AC. So that means that over here in terms of side, this length over here, if I call this A, oops, sorry, I'm using the wrong pen. If I call this A over here, if I call this B over here, and then if I call this C over here, and then if I call this D over here, then the conclusion is that A over D is equal to C over, A over B is equal to C over D. Okay, so that was the theorem from the last time, and we did a proof of it in the last video. So if you want to take a look at that, by all means, go ahead and do so. But the important thing that we got out of it was actually this thing over here on the right-hand side, what is known as the AA similarity, which basically says that if you have two triangles such that one angle is equal to another angle or congruent to another angle in the other triangle, And then you also have another angle that's congruent to another angle in the in the other triangle. Then the conclusion is that those two triangles are going to be similar to each other. So we literally just used theorem 1212 to prove the AA similarity, and that AA similarity is what the main thing that we want to get out of it. Okay, so now what we're going to do is we're going to go ahead and go back to these guys right here to help us prove that SSS similarity works and also SAS similarity works. So first what I need to do is I need to prove the converse of theorem 12.2 or 12-2. So this is going to be called theorem 12-3. Well, as you can see, not exactly a fun name for it, but it basically says that if you have a triangle and then you have D is going to be, again, a point in between, D is a point on the segment, and then F is another point on the other part of the segment. And this time the converse of it is given. So such that AD divided by AB is equal to AF divided by BC. So that means that over here on the right hand side, this length divided by this length over here is equal to this length divided by this length over here. Then the conclusion is that the converse of it, well, I need to prove that BC, which is the third side, is going to be parallel to DF, which is that segment that you're going to make in between. All right, so let's go ahead and prove this then. So the way we're going to do it is by an indirect proof. So we're going to go ahead and assume that DF is not parallel to BC. Okay, so that these two lines, we're going to assume that they are not going to be parallel to each other. Then in that case, what I'm going to do is I'm going to go ahead and say that DF is parallel to something else, which we'll go ahead and call it BC prime, where C prime is going to be on that length. So it's going to be on the side on the right-hand side over here. So you can see that C prime is somewhere on that side. And we're going to assume that DF over here is going to be parallel to BC prime over here. Well, if we go by that assumption, then that means that by theorem 12-2, then that means that AD divided by AB is equal to AF divided by AC prime. So then that means that we have the proportionality just using the theorem 12-2. If that's the case, then we can go ahead and say by transitivity that since these two over here are equal to each other or proportional to each other, then I am going to go ahead and take from the very get-go the given that this part over here, by transitivity, I can say that this is going to be linked up to all three of them. And if that's the case, now just look at the bottom part right here. This is the part that is going to tell us our conclusion. Since we have AC prime on the bottom and we have AC on the bottom, and remember, C prime is a point that's on the line AC or on the line segment AC. So then therefore C has to be the same thing as C prime because they are all on the same line. Okay, so there is going to be the converse of that theorem. Now, if you're wondering, okay, so why do we need the converse of this? Well, let's go back to the SAS and SSS situation, okay? So here, as we said, what's going to happen is for each one of these scenarios, we can overlap the triangles to see exactly what's happening. Let me take the blue triangle over here, and I'm going to overlap it as a result over here. And if you notice that when we overlap, you'll notice that the third side over here, they are going to be parallel to each other because of what we just said. See, notice over here, we have that 3 of a length, and then we have 6 of a length, and then we have 4 length right here and 8 length right there. So we're given that this has to be true. So by that converse, which is theorem 12-3, which we just proved, then we can say that these two sides are going to be parallel to each other. And if they're parallel to each other, then because of PCA, parallel implies that corresponding angles are congruent, then that means that this angle has to be congruent to this angle. And then finally, D is congruent to itself, so therefore these two triangles are going to be similar because of AA similarity. Okay, so we can always do that by just overlapping the two then. Okay, so let me go ahead and put that triangle back if possible. So here it is. And then now for the SAS similarity, well, it's just going to be exactly the same thing. I can take the smaller triangle and I'm going to go ahead and put it over here, right? Because they can overlap each other since the angle in between are congruent. Well, recall how I said that this length is supposed to be 6, and then this length is supposed to be 5. So according to my given, 6 over 12 is equal to 5 over 10. And then that means that the third opposite side right here should be parallel to each other. And once again, by PCA, then I can say that this angle is congruent to this angle. And therefore, by AA similarity, these two triangles have to be similar to each other then. Okay. All right, so there you go. That's going to be our proof. So hopefully that is something that's understandable. Trying to write this out using statement of reason is probably not ideal in this case. But anyhow, let's go ahead and try to apply these two, SAS similarity and also SSS similarity, and see how those work in terms of a proof. Okay, here's an example of a problem where you actually have to do a proof then. In this picture, here is what's given. We're given that these two triangles, ABC and triangle DEF, are going to be similar to each other. Now, X and Y are supposed to be the midpoints of AB and DE respectively, so you can see that in the picture right there. What I'd like to do is I want to prove that XBC, so meaning this triangle over here on the left, let me just go ahead and make this a little bit smaller. So XBC, which is this triangle over here, is going to be then similar to the triangle over here, which is YEF. So over here then. So given that those two big triangles are similar, I want to prove that the smaller triangles are going to be similar to each other. So I guess I'll go ahead and put a question mark over there. All right, so let's go ahead and start then. Now, first, we can go ahead and start by, well, what's given to us. And that is that the two triangles are similar to each other. So since the two triangles are similar to each other, the only thing that I can get from it by definition of proportionality for triangle is that AB divided by DE is equal to BC over EF. Now, I can go ahead and write the other parts, but I think this is the part that's important because technically, the other part, which, I'll go ahead and write just for your information, is the following, is equal to AC divided by DF. But I'm saying, hey, don't bother with this part because notice that the length AC and DF over here has nothing to do with the triangle that we're trying to deal with. So ideally, we will not want to deal with that, okay? Now, let's go ahead and play with what we have over here as a proportionality. Note that X is supposed to be the midpoint and Y is supposed to be the midpoint of DE and also AB then. So what that means is over here, my equation, I can go ahead and modify it. I can say that AB is equal to 2XB. And then also, let's see, how about DE is equal to 2 times YE? Because now we can go ahead and, I guess, move into the smaller triangle and start showing that there are some things that are going to be proportional to each other. By substitution, then that means that we have now 2XB divided by 2YE is equal to BC over EF. So that is going to be by a substitution. And when we do that, we can divide by 2, and now we have this proportionality. Well, that as of right now is basically saying that this guy over this guy is equal to this guy over this guy. Hey, that's kind of good because that is a similarity that I want. Looking at what we have, we can easily show that XC divided by YF is going to be proportional to all of that. But I think the easiest way is to just say that angle B is going to be congruent to angle E because remember, those two big triangles are going to be similar to each other. So we can say, right, by corresponding parts of similar triangles are congruent in this case. CPSTC, again, this is kind of like a thing that is unofficial in all textbooks. It's just something that I kind of made up, which is kind of like CPCTC. We can say that angle B is going to be congruent to angle E. And now taking what we have right here and taking what we derived over here, we can now say by SAS similarity, okay, then that means that triangle XBC is going to be similar to triangle YEF. And then we are going to be done. All right, so, the proof hopefully isn't too bad. All right, let's try look at a few more. Here, this one is pretty unique. It's actually a very interesting proof, which we can actually use in the future. Here it says that if you have a triangle, right, and the triangle is going to have an angle bisector, which, all triangles should have some sort of angle bisector. It turns out that the angle bisector breaks the segments of the triangles into some sort of proportionality. And the way it works is that you have the following. So here's AD, which is going to be my angle bisector. I want to prove that A over here divided by B is going to be equal to X divided by Y. So in short here, let me just see if I can try to draw a triangle over here. So it's the case where if you're going to have an angle bisector like so, then that means that if this is going to be 4 and then this is 5, then this guy over here is probably going to be something like, say, 12, and then this is going to be 15 then. Okay, so that's what this theorem is about. It's actually a theorem in the textbook. All right, so let's go ahead and try to prove this one. Now, the proof of this is not going to be very, very simple because it's not something that you would normally see. You're going to have to actually introduce something. So the thing that we're going to have to introduce over here is a point Q on BA, the ray, such that QC is going to be parallel to AD. So let me go ahead and see if I can draw that in there. Okay, so I'm going to go ahead and take BA, and I'm going to go ahead and extend it like so to some point Q on there, such that QC is going to be parallel to AD. So here is going to be my point Q, and that point is going to be at the location such that these two are going to be parallel to each other. And I think you get an idea as to what I'm trying to set up here. Well, now that we know that these two are going to be there because of the parallel part, then I can probably show that certain triangles are going to be similar to each other, right? Note how because of parallel, then that means that this angle over here, angle ADB, should be then parallel. So then that means should be congruent to this angle over here, QCB. Okay, so by PCA, then that means that angle D is congruent to angle C. And also by the reflexive property, then we can say that angle B is is congruent to itself then. So then the conclusion is by AA similarity, I can now say that triangle BAD is similar to triangle BQC. So meaning that the smaller triangle located right here is going to be similar to the bigger triangle that is located right here. All right. So let's see if we can kind of write out some sort of result from that then. Okay. So then because the two triangles are similar to each other, so we can now say that by definition, right, of similar triangles, then that means that BA divided by AQ is equal to BD divided by DC. Okay, and just to make it a little bit easier, let's go ahead and implement the A, B, and X and Y in there so you can kind of see how that works. BA is the A part, so that means it's A over here. AQ is still going to be AQ, so we don't have a name for it, so we'll just go ahead and call it AQ. BD is going to be B over here, and then Y is supposed to be DC, so that's there. So we just need to somehow show that AQ over here is going to be the same thing as X. If I can somehow show that it's X, then we are pretty much done. Now, AQ in the picture is going to be this length over here. Let me just go ahead and draw a little bit better. So here's AQ, right? How do I know that this guy is the same as X? So that's going to be my question mark. Well, this is where we're going to have to do a little bit of sneaking in, but I think we can definitely see it. Okay. Here, let me go ahead and look at some of these angles that we've kind of created as a result of this triangle. Now, here you can see that this angle should be congruent to this angle right here because of PAI. Okay, so this angle right here, one of the angle bisectors, should be congruent to this angle by PAI because the sides are parallel to each other. Then for the other angle, right, the other angle bisector right here, that I feel like it should be congruent to this part right here because of PCA, right? Because this angle and this angle, they're corresponding angles and they are congruent because the AD and also QC are parallel. So, hey, look at that. If this angle now is congruent to this angle, then that means by the isosceles triangle theorem, then that means that this x right here and this x right here should be one and the same. So now I can go ahead and replace AQ with x. And if I cross multiply my equation right here, so A divided by B is equal to x divided by y, that is going to be the result that we were wanting. And there you go. Okay. All right, so here is the last one right here, a little bit lengthy, but we're almost done. Now, in this last example, I think this one's going to be pretty easy. Maybe you're going to give it a shot yourself. But here, talking about transversal, going back to last semester, turns out that there's a proportionality that you can get out of it too. So given in this case that you have three lines that are going to be parallel to each other. Line 1 is parallel to line 2 is parallel to line 3, as you can see in the picture. T1 and T2, those are transversal, so that means they cut those parallel lines. I want to prove that A divided by B is equal to X divided by Y. So A over B is equal to X over Y. Well, thinking back to what we did in the transversal case, here is going to be the hint that I can kind of give you, and maybe you can pause the video and try to figure it out yourself. I'm going to go ahead and introduce a third transversal, maybe some guy that looks something like this over here, right? Hopefully you can kind of see as to what's happening. At this point, if you want to pause it and try for yourself, then go ahead and do so. But if not, let's go ahead and write the proof. Let me go ahead and call this segment over here M, okay? And this segment over here, that is going to be called N. Well, we know that line 1 and line 2 are parallel to each other. So then that means that A over B should be equal to M over N because of, let's see, I think it was like Theorem 12-2, right? Because remember, if they're parallel, then that means that we have a proportionality. Then if you look at the 2 on the bottom, right, L2, that is parallel to L3. So that means that M over N is equal to X over Y. So now we can go ahead and use a transitive property. So then that will lead us into our conclusion. Well, there you go. Thank you so much for watching. And I will see you guys next time then. Okay, take care. Bye-bye.